Hi, welcome to the tutorial on assumptions of linear regression. By the end of this tutorial, you will be able to list and explain various assumptions of linear regression model. So far, we have learned what is a linear regression model, how it is represented using the equation of a line, about the parameters of the line and how to find them manually using cost function curve, how gradient descent works intuitively and mathematically, and we also implement it in Python. Now in this tutorial, we are going to learn about the assumptions of linear regression which must be satisfied so that the linear regression can produce desired results. So let's dive right into it. The first assumption for the linear regression is the most obvious one. The target and the independent variable should have a linear relationship between them. It need not be a perfect linear relation, that is, correlation equal to 1 in the strictest sense, but should follow a fundamental property of a linear relation. Now, what is this fundamental property of a linear relation? You might ask. In a linear relation, y changes with x, and for every change of delta x, the quantum of change in y, that is delta y, should be similar irrespective of the value of x. That is, if x equal to x1, a change of delta x causes delta y change in value of y, then at x equal to x2, also a change of delta x should cause a similar change as delta y. But you might ask why we cannot use linear regression on the non-linear data. For this, let's consider non-linear data as shown on the screen. Now, as you can see in this data, initially y changes rapidly with change in x, but at higher values of x, the change in y is not significant and hence the fundamental property of linear relation is not met. Now, what do you think would be the result if we apply the linear regression to this data? Let's do that and find out. A regression line on this data would look something like as shown on the screen. We can clearly see that generalizing this data with a straight line is not the best idea because it will not only generate large error, but the inferences about the data that we will extract will not be reliable as linear regression will fail to model the pattern mathematically. For example, the linear regression will continue to predict higher values of y at higher values of x, while in reality, that is not the case. Now you might be asking, so what can we do if the data does not have a linear relation? The trick to make the non-linear relationship linear by using variable transformation operations, such as x square, root of x, log of x. So maybe x does not have a linear relationship with y, but x square or root of x or log of x could, and hence we should model that. We will be covering this in detail later. Next assumption of the linear regression is that error terms have constant variance. It is also known as homoscedasticity. Let us consider this residual plot. The red line here represents the regression line or the predicted values, since predicted values residual with respect to themselves would be 0. Each gray dot represents an individual error term. If we were to draw the blue lines as contours to show the spread of the error terms, the distance between the regression line and the blue line represents the variance of the errors with respect to the regression line. And if we look closely, the variance of the errors is increasing as we go from left to right in this given plot. This is called heteroscedasticity. This may arise because the relationship between x and y is not linear and or due to the presence of outliers. To counter this problem, other than treating outliers as we saw previously, we often transform our data using the transformation methods such as log of x, root of x and x square. Now, for example, if we were to transform our data using log function and then plot the residual plot, we would get a plot as shown on the right side of the screen. We can clearly see that in this plot, the variance of the errors is nearly constant throughout the data. Now we have discussed 2 assumptions of linear regression. That's enough for now. We will discuss 3 more assumptions of linear regression in the next video. See you there.